What the heck?
Hectagon.
Boy, oh boy, my hair sure is getting big. It's never been this long, I think, ever. It's gonna like start hanging down under its own weight soon. Crazy stuff, man. I'm not getting a haircut for a while, I suppose. In the meantime, I'll just drink a lot of coffee like I usually do.
Wacky Calc Wednesday!
So I've been reading, recently, I finished the book by Edward Snowden. I'm reading Stanislav Ulam's Adventures of a Mathematician right now. This is a original copy from 1976. It's 45 years old. I got it at a little book fair about a year ago. A lot of the pages are torn. The pages are really easy to tear. It's very yellowed and like maybe a little water damage from the air, but it smells amazing and it's very interesting. It's a great, great read so far. I'm only about 60, 70 pages in, but I'm having a great time learning about this most interesting man, and so I recommend reading this book. Today I have a bonkers integral for you. Some might even say bonkers and yonkers. It's truly a gem of just an amalgamation of just some wacky looking functions put together, hence Wacky Calc Wednesday, of course. It, of course, has to do with the Lambert W function, just like the oily macaroni constant. I'm on this trend now, because there's so much to learn, so much to do, and just like that really strange integral that came out to be something to do with the omega constant in the end, this one is another one of those integrals that's on the Lambert W function Wikipedia page that's sort of just on there, and even the link you go to just takes you to, like, a poster, and that's, like, the citation, like that's the citation, that it's just a picture of a poster with information about the W function on it, and that integral is on it, and they're like, this is the citation, this is the proof that this is true. And you can plot it in Desmos and it does work. But today I'm going to prove it in the best of my ability. And it's a really beautiful, beautiful demonstration of contour integrals in the residue theorem. So, without further ado, let's get to it. Enjoy the strangest integral I've ever understood. So, before we start with our beautiful result, we need to establish a few facts about the Lambert W function. And that should take us a little while, but then we'll get to the final beautiful answer in the end, I assure you. So we need to sort of start with some assumptions. So let z equal x plus iy. So this is going to be in the world of complex numbers. I did mention doing contour integrals before, so this will involve complex numbers. And we will also let w of z equal some other complex number, u plus iv, right? So I is, of course, the square root of -1, or one of the square roots of -1, the principal root. And, of course, w of z is the inverse of z times e to the z, right? So if you have this function undoes it after you've picked the branch. The assumption throughout this video is that we will only be looking at the principal branch of the w function, so w sub 0 of z, so I won't bother writing the 0. This is the principal branch with the branch cut. Study the Lambert W function in any way, you'll understand that the principal branch is analytic everywhere on the complex plane, except for this branch cut right here, along the real axis. Right? So it's got a branch point at -1 over e, and that branch cut goes all the way to -infinity. And we're essentially going to be exploiting this branch cut by doing a contour integral that reduces to an integral over this infinite, or an improper integral over this interval here. But first we need to establish some things, so these are our assumptions. Now, because the w function is the inverse of z times e to the z, what we can do is actually write z as w of z times e to the w of z, by definition, right? It is the inverse function, so plugging the inverse into the original function just gives you the input back, which is z, of course. But now what we should do is replace z with x plus iy and w of z with u plus iv, so that we can sort of put things into real and imaginary parts. So this implies that x plus iy is equal to u plus iv times e to the u plus iv. right? That's the assumption based on what we defined them to be at the beginning. And now what we're going to do is we're going to solve for x and we're going to solve for y in terms of u and v, right? Because we want to get the real and imaginary parts of the Lambert W function. So how do we do this? Well, we need to sort of come up with a bunch of complex number terms and real number terms that we can then distribute into each other and get each of the real and imaginary parts. So first of all, exponentials, the property that they turn sums of the input into products of the outputs, that still holds for complex numbers. So we can rewrite this as u plus iv times e to the u times e to the iv. Now, of course, I will link you to my proof of Euler's formula that I did on this channel, because of course if there's any proof of it I want you to watch, it's the one that I did. And so we're just going to replace e to the iv with what we know it to be equal to, which is of course cosine of v plus I times the sine of v. Because this is always true. This is a perfectly entire function, so this is an always true relationship. I really highly recommend Grant Sanderson / 3 Blue 1 Brown's recent stream on this particular topic, because he does a great job illustrating using his, I think it's called Manim or something like that, Manim program, that this actually is a periodic function, and it does converge no matter how big of a v you plug in. It will always land somewhere on the unit circle, and it's quite remarkable to see it in that context. Because the assumption is that x, y, u, and v are all real numbers, so let's just make that clear. So x, y, u, v are all some real numbers, right? That's the whole point of splitting something up into its real and imaginary parts, because you want I to be multiplied by some real number, and then there's the other real number that's not being multiplied by I. In that case, e to the u is a strictly real number, right? It's somewhere between, it's something greater than 0. Strictly greater than 0, right? Because u is real, and e to any real number gives a number that is strictly greater than 0. So what we need to worry about is really foiling out u plus iv and cosine of v plus I sine of v. And when we distribute those things out, we end up with e to the u multiplied onto everything. It's just sort of there for the ride. And then we have u times cosine of v plus I times u times the sine of v plus I times v times the cosine of v, right? We're just foiling. Plus I squared times v times sine of v. But what's I squared? I squared is -1. So we get minus v times sine of v. And now we're just going to collect real and imaginary parts. This whole thing is equal to x plus iy. So x is going to be equal to all the stuff that's just stuff that's not multiplied by I. So we know, therefore, we have that x, which again is the real part of z, this is equal to e to the u times u cosine v minus v sine v. And y, being the imaginary part of z, which is again the part that's the real number that is being multiplied by I as part of the complex number, is equal to e to the u times u sine v plus v cosine v, because the I is just being factored out of these two numbers, and we're sort of just talking about the real number that is y, right? Not focusing on the I. So e to the u times the quantity u sine v plus v cosine v, which is just sort of a neat little collection of stuff. There's a few things that I want to investigate. We also need to remember for later on that the derivative of the w function is this. So the derivative with respect to z of the w function is equal to the w function divided by z times 1 plus the w function. This is the derivative of the Lambert W function with respect to z. And what's important about this is that we are able to break the w function up into its imaginary bits, and the number z up into its imaginary bits as well. Or, I'm sorry, real and imaginary bits. So we'll need to know that for later. What I also want to investigate is what happens if we plug in the conjugate of z. So not x plus iy, but x minus iy. So what we're going to do is with those facts, we're going to investigate a couple of things. So we're going to erase all of these assumptions now. We've just shown what we wanted to show with regards to the real and imaginary parts of the Lambert W function. Now let's explore some of their properties. So first what I want to show is this. So claim. I want to show that w of the conjugate of z is equal to the conjugate of w of z. In other words, if z equals x plus iy and w of z equals u plus iv, I want to show then that w of x minus iy is equal to u minus iv. So plugging in the negative imaginary part for the input is identical to getting the negative imaginary part for the output. Essentially what the idea is, given these two relationships here that we just derived, I want to show that plugging in negative v into both of these will result in x remaining the same and y becoming negative, because then that would demonstrate this relationship here, that plugging in the conjugate gets you the conjugate out. So let's plug in negative v wherever we see it. So we'll get negative v right there, and we have a minus negative v times the sine of negative v, right? All I'm doing is plugging in a negative v wherever I see it, so that we're getting the conjugate out, which shows that we would get the same thing if we plugged the conjugate in. Plus negative v times the cosine of negative v. And all we're going to utilize is the even and odd properties of the sine and cosine function. So we know that cosine of a negative number is the same as cosine of the positive number, because cosine is an even function. So cosine of negative v is identical to cosine of v. So we actually don't need to worry about those, right? We can just write them as they were. And the other thing is that sine of a negative number is equal to negative the sine of the positive number, because sine is odd. So if we have sine of negative v, that's going to be the same as negative sine of v. So we can simply replace every sine of negative v with negative sine of v, and that's perfectly valid, like so. I hope that's clear. And now we're going to use the negatives to cancel some things, because what do we have? We can use this negative to cancel that negative, and we can factor out these negatives to bring them out to the front. So make these positive and make the outside negative. Notice we get v sine v like we had before, and you'll notice that plugging in negative v does not change what x is. X is still positive. But if we plug in negative v for the imaginary part, we can just bring this negative to the other side, and we see that we actually result in the same thing, but we get negative y, which means that plugging in negative v for the output gives you the conjugate for the input. And we could have done the same by starting with negative y, moving the negative over, and seeing that we plug in, we get all the negative stuff for the negative v, and we would see that the same thing would happen here, and that plugging in negative v here doesn't change x. So the point is that we're proving this theorem right here, that plugging in a conjugate into the w function gives you the conjugate of the w function. So we're going to need to utilize that fact later. Now we're going to do a couple more exploratory things. We're going to ask ourselves, what if this number z is purely imaginary or purely real? So let's say, what if x equals real part of z equals 0? Question. And what if y equals imaginary part of z equals 0? Okay, so if x equals 0, that means that 0 equals e to the u times u cosine of v minus v sine of v. Now, e to the u, remember, is a real number. We have e raised to a real number, and that is always strictly greater than 0. So this cannot be the factor that's equal to 0, which means the only thing that can be 0 is this factor right here. So we should just set this equal to 0, and see if we can come up with a cool relationship. Well, if we set this equal to 0 and add v sine v over to the other side, we end up with u times cosine of v is equal to v sine of v. Dividing cosine of v on the other side, we get that the real part of the output, u, is equal to this function of the imaginary output, v. The imaginary part of the output, v. And we get v sine v over cosine v. Sine v over cosine v is the tangent of v, so we get v times the tangent of v. So if we assume that the real number that we're plugging in, I'm sorry, if we assume that the number we're plugging into the Lambert W function is strictly imaginary, then we come to the conclusion that the real part of the output is equal to the imaginary part of the output times the tangent of the imaginary part of the output, which is a rather interesting relationship there. So this actually shows you that you can write the image of the imaginary axis for the Lambert W function in terms of tangent, which is quite an interesting fact. And the other thing that allows us to derive is it allows us to find a representation for the imaginary part all in terms of v. Because remember, the imaginary part is y equals e to the u times u times the sine of v plus v times the cosine of v. right? And so now we know that u can be written as v times tangent of v, so we simply have to plug that into this equation. So we get e to the v times tan v times tan v times sine v plus v cosine v. I know this is a little symbol heavy, but it's about to simplify drastically. So this has a common factor of v, so we can pull that out to the front. And we can write tangent of v as sine over cosine, which means that this product here becomes sine squared over cosine. So we can write this as sine squared over cosine. And we can write cosine as cosine squared over cosine, simply by multiplying the top and the bottom by the cosine of v. So we get cosine squared of v over cosine of v. Now, because these have the same denominator, I can combine them, and I get sine squared of v plus cosine squared of v in the numerator, and that's of course a Pythagorean identity, and that is always equal to 1, no matter what v is. So then we're just left with 1 over cosine of v, which is the same thing as the secant of v. So this simplifies amazingly to v times the secant of v times e to the power of v times the tangent of v. So we're assuming that if the input into the W function is purely imaginary, then the real part of that output can be written as v times the tangent of v, where v is the imaginary part of the output, and the imaginary part of the input, the only part that matters because we're assuming that it's purely imaginary, can also be written entirely in terms of the imaginary part of the output. That tells us that this is the true relationship here. So we have that W of v times the secant of v times e to the power of v times the tangent of v is all equal to v tan v plus I times v, which is just lovely, right? So that tells you that this is the image of the this is essentially the imaginary part of the input, assuming that the input is purely imaginary, and then this is the image of that, right? So quite a cool parametric curve, I think, if you were to take a look at it. It's something called like when we get to this part, it'll be in terms of the cotangent and the image of the real number line. And I think it's called like the trisectrix of Hipparchus or something like that. Sort of a weird parametric curve. Has to do with, can be used as an extra tool that allows you to trisect an angle or square the circle, actually. So it's outside of the realm of constructibility using just compass and straight edge, but it's something to do with this curve allows you to trisect an angle, which is just brilliant. So we're done with the imaginary side. Now we're going to assume, what if the input is purely real, right? The imaginary part is 0. And this is the one that we're actually going to be used for the purposes of this video. So instead of setting the real part equal to 0, we're going to set the imaginary part equal to 0. So we get 0 equals e to the u times u sine of v plus v times the cosine of v. Now again, e to the u is a purely real number, and u is a purely real number, which means e to the u must be strictly greater than 0. So this is not the problem. This is not the thing that's being equal to 0. This is the part that has to be equal to 0. So setting this equal to 0 and subtracting v cosine v to the other side, we get that u times the sine of v is equal to negative v times the cosine of v. Dividing sine of v over, we get that the real part of the output, assuming that the input is real, we get that u is equal to negative v cosine v divided by the sine of v. Using other trig functions, we get that this is negative v times the cotangent of v. Plugging this in to the real part, right? Into the imaginary part, we get that, plugging this representation of u into the real part of the input, which is x, right? We get that x is equal to e to the negative v cotangent of v times negative v cotangent of v times the cosine of v minus v times the sine of v. Right, so all we're doing is plugging this representation for the real part of the output into the real part of the input, wherever we saw a u. And we're going to use the exact same trick that we did before. There's a common factor of negative v, and we can write cotangent as cosine over sine, which makes this part cosine squared over sine. We'll write sine as sine squared over sine, and then we'll end up with sine squared plus cosine squared, which is 1, divided by sine. So we'll end up with the cosecant of v in the end. So if you want to feel free to work that out on your own, we end up with negative v times the cosecant of v times e to the negative v times the cotangent of v. And now this representation of the real part of the input, assuming that it is purely real to begin with, this is going to appear in our final integral representation. And so if you've seen this before, you should find this expression a little familiar. This is going to be part of how we essentially solve this problem. So now this is the side we're going to need to use. We're not actually going to use this, though it's interesting and maybe even a little bit more elegant because it's not got negatives and it's got, well, tangent and secant. Maybe tangent is a little more familiar than cotangent, but you know, if you're well versed in these functions, it shouldn't really make a difference. This is the side we're going to need for our integral. Because we actually need to assume that our input is going to be purely real, with a zero, an imaginary part equal to 0, and then that way this is going to come into play in our integral. So, speaking of the integral, which integral are we going to use? Well, we need to establish one more general fact, and then we'll get to the contour, because it's a beautiful contour. We need to establish something rather interesting. So we want to assume we have some function f of z. Given f of z, such that f of 0 equals 0, and we have a defined inverse. So the inverse of z is, the inverse of f is just some function, and we can talk about it and we can utilize that function. That's all. That's all we need. And that also means, of course, that f inverse of 0 equals 0, so that's the sort of the important bit. So if we have this weird-looking function here, so x times f prime of x divided by f of x times f of x minus z, where z is some complex number, dx. X is not necessarily a real number, it's just the dummy the dummy variable for the integral. So let's assume we have this integral right here in terms of this function f of x that has, or f of z that has these properties. I only wrote this here, so this exists, right? F inverse exists, it's some function, it's going to be useful to us. And what we're going to do is we're going to make a u substitution. We're going to let x equal f inverse of t, which is to say that f of x is equal to t, which implies that f prime of x dx is equal to dt. So we're essentially just doing a substitution. And so our new integral is going to look like this over the same contour. F prime of x times dx, that's going to be dt. So we can write that over here. And x is going to be replaced with f inverse of t. Right? And let's call this I sub f, by the way. So given some function f, this integral I is what we're trying to solve for. Now f of x is going to be replaced with t. F of x is going to be replaced with t minus z. And we're assuming that this function, f and f inverse, are analytic within and on this closed contour C, whatever it is. Given that, we are, and I apologize, this should have been 1 over 2 pi I times this integral. My mistake. I forgot this factor, because we're going to need to utilize the residue theorem, so I hope anybody who's seen complex analysis sort of understands where that's coming from. If not, you will in a moment. So we have to remember to divide by 2 pi I, because we're going to use the residue theorem that says we need to take the residues of this function here and sort of see if we can establish what this contour integral is. Remember I said that f of z, and therefore f inverse, is analytic in this contour and on this contour. So the number 0 and the number z are going to be the only things that cause a problem for this integrand, and so they're the only poles that we need to consider. So we need to do the residue at t equals 0, so we'll end up with, so remember we have that factor of 2 pi I out the front, times this factor of 2 pi I in the denominator. That's why we had to assume the 2 pi I is out the front, so that we can cancel it with the 2 pi I that comes with the residue theorem. And then we need to get rid of the factor in the denominator that would be a problem at 0, and then plug in 0 to the rest of it. So we get f inverse of 0 divided by 0 minus z. And then we need to get rid of the factor that has z as a problem and plug in z into the rest of it. So we get plus f inverse of z divided by z. And since f of 0 is 0, that means that f inverse of 0 is 0. We're also assuming that that z is not 0, by the way. Z is a non-zero number. And so that term goes away. The 2 pi i's cancel each other. And we're just left with f inverse of z divided by z. So perhaps you'd be inclined to multiply the z over just to get a well-defined version of f inverse. So we're multiplying that over. Now, this is the thing we're going to utilize to calculate this incredible integral representation of the Lambert W function, though it may seem a little circular, right? We're using the function, the inverse function, to define, we're using the inverse function under the integral to define it as a function outside of the integral. And so that's a little circular, yes, but the input of the function under the integrand is not the input outside the integrand. The input of the function in the integrand is the dummy variable, and the input for the actual function that's defining it are these two z's right here, right? So we're not really using the function to define itself, it's simply part of the integrand. And we'll actually see that it will go away when we do this particular example of the W function, given the real and imaginary parts that we solved for. So now that we've finally gotten through all the preliminary stuff, let's finally show what the contour is and how we're going to solve this integral.